Okay, so we have finished up the probability section of the class, and now we're going to work our way into statistics. This is, of course, what I'm the most interested in since I teach statistics normally all semester long, particularly in Math 220. While we are going to try to keep it oriented towards a lot of what you would do with your future students, we are definitely taking this up also to the college level. And unfortunately, sometimes statistics does not have the same language in the K through 8 system as it does in the college level classroom. So as we go through some various graphs and things, I'll try to point out some of the things that you might see differently when you're teaching 4th or 5th grade. A lot of these topics are also absolutely part of the Algebra 1 curriculum, in case you'll be teaching that. Anything I ever present to you in Math 207 is coming from the majority accepted college level statistics curriculum. So maybe unlike math educators, that is my target as opposed to the K through 8. So just to have that disclaimer. I have loaded the packet of notes to go along with this video, whether you're just following along, whether you're taking your own notes, or actually printing out the packet. In the packet, there is going to be a small activity we do, so you're going to need to have it up on your screen or printed. And not only for this video, but another one that's going to be coming up, I always collect survey data, and while I could have done that with you guys through a Qualtrics survey, to be honest, I am making this video about a month before Maymester starts, so I cannot collect data from you. So we are using the survey data I collected spring 2020 from my Math 207 students, and that's what this is, and we'll be using this again in a couple of different videos. So definitely an important piece of paper. Usually I'll start off with some introduction of bad statistics. My big thing when I teach any statistics class is that stats is not just to learn for a particular grade level or because you're in AP stats in high school. It really relates to every single person's life. We are bombarded with information through media and radio and Facebook. And so much of it is wrong, and I'm not even talking about political fake news. So people have to start moving past their knee-jerk response. That's what I call it when you first hear something, you're like, oh, that's cool. It's okay to have that initial reaction, but just to put 30 seconds of thought into, is this true? Is it from a reliable source? Could it be something else? Just thinking through it for 30 seconds before you hit retweet or share on Facebook or that type of thing. So I think I may wait till the end of this video just to show you a few of those things. Homework. I don't think this is part of the packet, so make sure you write this down. If at any point during Maymester you hear about an Excel homework, we are not doing that for Maymester, so completely ignore that. You do want to be working on chapter 30.1, those particular problems. A few of the problems say use technology. You do not have to use technology. You can just do the stuff by hand. At the end of this video, we're going to be talking about pie charts, which are not that different from spinners. So your book, again, I think tells you to use technology. You do not have to do that. Just calculate the degrees of each slice anytime the book homework is asking for pie charts. And then chapter 29.4, whatever is listed. I have that homework assignment sheet loaded on Canvas, and it tells you by chapter, hand-picked problems I picked out. So whatever I picked out, do those. All right, let's start with some basic definitions. And again, I'm just writing really what's from the notes. And I've already messed up. I I get to erase. Hopefully you can too. I knew I messed up because I love this definition. I found this in a different book, and I love that in one sentence they were able to put everything in it. Most of the time when you ask people, about statistics, they know it has to do with data or making graphs or whatever. Actually, I love that this book put, well, first of all, art and science. It's definitely a science. You're going to see when we do some of our graphs that on some of them you're going to have a little bit of freedom, and that's really how I view the art part. Art and science of designing studies, that is the most critical part. And then analyzing the data that you get back out. So many people forget about the design phase. Now, we are barely going to talk about that. Their entire course is called Design of Experiments, but it's just the whole junk in, junk out. If you do not collect your data in the appropriate way, sure, you're going to get data and you can make graphs all day long, but it's unethical and it's misleading because it means nothing. So let's just do a few highlights, and some of the highlights that I give you now are going to be talked about more through the next few weeks, or, well, it's Maymester, I guess, the next week, right? So just a couple highlights for design. Ideally, and this is hard in real life, you need random representative samples. So, this would work so much better if you guys were in front of me. We could have conversations, right? But I have to almost just try to recreate conversations with myself. Trying to pick up the survey data. Last spring, I just passed around a piece of paper and had them fill it out, right? They were my 207 students. They were sitting in front of me. It was very convenient and easy for me to collect this data from them. I passed around a piece of paper, right? So they definitely weren't random. They just happened to be the ones in my class. Think about whether, or even you guys, Math 207 students, are you representative of JMU? You definitely go to JMU, but hopefully everybody knows you're not necessarily representative. You are absolutely all one major. What has that got to do with anything? Well, I'm not sure. It depends on what data we're collecting. Maybe you have a different perspective on some survey question or different experience leading up to, a particular course or whatever. So in the JMU bubble, it would be very easy to get random samples. I could ask the registrar to, randomly select students with at least 70 credits or less than 30 credits, whatever. But can you imagine even just for Rockingham County how difficult that gets, or to the state of Virginia, or to the United States? So while, yes, we need that, sometimes, unfortunately, in real life, it's nearly impossible to do that perfectly. Controlling for other variables. Sometimes these are called lurking or third variables. You do not need to know those words. But maybe just a quick example comes from my bad stats. I was driving to JMU a few years ago listening to the local radio, and they were talking about some study. And think about it, a DJ is talking about this, right? This was not any formal NPR show. But he was saying how there had been a study published that said playing golf helps men live longer. Playing golf helps men live longer. So just to get you in the habit of what I mean by moving past your knee jerk, my first thought was, oh, probably. So think about some good things about playing golf. All right, some of the answers normally that you guys will tell me is it's outside, it's fresh air, it's some exercise. I mean, hopefully if they're walking and not taking the golf cart, it is exercise, right? There's a social aspect to it. There's lots of good, it's stress relieving, relaxing, all of that. And those are all good things that you could imagine helping someone live longer. But after about 30 seconds when I was in my car, I started questioning it. And you guys are young, but I don't know that just walking is the end all to health, particularly if you're a female. I know this was a study on men. They definitely talk about strength training, to help osteoporosis, all this other stuff. So I started thinking, I don't know that golf is the end all exercise. So then I tried to start brainstorming why else could they have seen these results? Because I'm assuming they did see these results, that playing golf helps men live longer. Now, I want you to know when I ask y'all to brainstorm, I might be wrong and you might be wrong. It's just the idea that we're starting to think. We're practicing thinking. I have never pulled up the original study to see if they actually, address these issues I'm about to bring up. But there is an assumption they were talking about playing golf regularly, right? Not just once every 2 years. Even if you play golf on a public golf course regularly, it takes a lot of money. What's money got to do with it? Well, living longer. Let's see, money can buy health insurance, so you can go to the doctor to help prevent things from, health issues before they get too big. It can buy medicine. It can buy food, healthy food. Obviously, it buys shelter. Having some money is a stress reliever in and of itself. So I'm wondering if this was not related to socioeconomic status, that instead of having golf related to men living longer, maybe both of these were related to socioeconomic status. So that's what I mean by thinking. That's what this means. Controlling for other variables. I wonder if the study controlled for the socioeconomic status, and that would have been part of the design. And that's all the really complicated stuff we're definitely not going to talk about. But just when you hear stuff, don't take it at face value. Think about, oh, well, maybe it's this or maybe it's that. All right. Second piece. All books, sometimes they'll call this the first branch of statistics. You don't have to know that, but it's always a big thing they talk about, descriptive statistics. So there's this whole branch of stats called descriptive stats. It's pretty much what you guys are going to be doing with your K through 8 students. It's mostly, if not all, of what we do in Math 207. No one wants to look at raw data. Just to let you know, this side of the data sheet is by student, but to make it a little bit easier when we're in the classroom or making a video, this is by column. I asked them how many Facebook friends they had, Instagram followers, Twitter followers, do you like cats, do you like dogs, do you wear glasses? So even if I'm just looking at that data, I think there were maybe 45 students or something, I still have a very hard time wrapping my mind around what I'm seeing. So that's why we make graphs. We might state what the mean or the median is, things like that. Definitely does not take a statistician to do descriptive statistics. Tons of software will do it for us, but as easy as it is, it gets screwed up all the time, and I have lots of examples to show you of that in this video. Inferential statistics, that's the much more interesting topic. If you come back and take Math 307, some of that is absolutely included in Math 307. It's the ability, and we actually really do have this ability, to make predictions or conclusions on the population based solely on sample data. So again, this all assumes you have correct design, right? But this means that, assuming I designed it right, I can sample 50 JMU students and make a statement about all 20,000. You're going to see this come up all the time in the next few months since it's election year. All of the polls, when people start running for president and that type of thing, they are all based on about 1,000 registered voters, and they are trying to make a statement about all voters. That is the default for political polls. It's 1,000 registered voters. Likely voters would actually be more useful. Sometimes you'll see those because we don't really care if you're registered if you're not actually going to vote, right? But that idea that I can just take a sample of 1,000 and make a statement about, I don't know, 150, 200 million, however many voters there are in the U.S., that's pretty amazing. But the big thing that we kind of have to accept on the first day of stats is, well, I did not go ask 150 million people. I only asked 1,000 or whatever. I have incomplete data, meaning we run the risk of being wrong. Let me start to write some of that. And of course, our samples are going to vary. If you got a different group of 50, they could have different results, right? Or a different group of 1,000 registered voters. So samples vary, and we have incomplete data. So thus, we run the risk of being wrong. Just to let you know, it's about a 5% chance, no more than a 10% chance. We don't study where that number comes from in 207, but I just want to make sure you know, we keep it small. It's not like there's a 40% chance. Then why do we do it then? Why do we take samples? This is normally when I let y'all brainstorm. And it always, of course, comes down to time and money. And of course, they're both interrelated, right? I guess if you had a lot of money, you could buy enough of a workforce to cut down on the time, but those I know are very interrelated. How much trouble and the logistics to get all 20,000 JMU students to answer me? Or think about how long is it going to take you to go survey 150 million registered voters? Way too long. The election would probably have been over a year before that. Again, all incorporated into this time and money, and particularly, again, since it's election year, there's a relevancy issue. When they want to tell us on some given day in October, who's in the lead for the presidential race, they have about 24 hours to collect that data and put it on our TV. They have to somehow do this in 24 hours. There's no way they're going to get to all the voters. If they had to get through all the voters and come back a year later and say, oh, last October, this is what y'all were thinking, it would be completely irrelevant. We would have already elected a president, right? So I'm going extreme here, but what I call the pulse of America, even if it's like, what do you think about the president's speech last night? They have about 12 hours to get that information into a graphic onto your television the next day. So samples are the only thing that they have. Sort of a, again, subset of all this, but when I was at Georgia Tech, I guess you would call it my concentration when I was getting my master's in statistics was quality control. usually right here I try to bring in two local things to kind of tell a little story on. So related to quality control and also destructive studies. Let's see. First quick example, there is the Hershey chocolate plant about 40 miles south of JMU, and they make the Reese's Cups candy bar there. If you've never thought about a Reese's Cup, it's a very specialized candy bar. There are two of those circular things, and each wafer, or whatever you want to call it, is a layer of chocolate, peanut butter chocolate. It's crimped at the top. The two little wafer things are then put in a very cute white cardboard. No, each one is put into that brown paper wrapping. Then it's put into the white cardboard thing. Then it's put into the orange wrapper. And that orange wrapper is actually wrapped perfectly when you flip it over, kind of like how you're supposed to wrap Christmas presents. So very complicated candy bar. And I was able to watch them make the candy bar at the factory one day. First, there were people who were just watching the candy bars come off the machines, and they're picking out the ugly looking ones. And they stand there all day long, and they pick out the ugly ones, and they put them in a bin. I'm not really sure where it goes from there. The ones that make it past that, they get wrapped up, they get put in boxes of probably, 30 or whatever, and sent to the grocery store. But, so some of that quality control is built in just visual, right? They're picking out the ugly ones. And I'm sure someone visually looks at them once they're wrapped in the orange paper, make sure they look pretty, because you're not going to buy an ugly candy bar, right? That's all visual. But at least once per shift, per assembly line, they're going to take a batch of these candy bars back to the lab, and they're going to dissect them. I don't really know, they didn't let me watch that, but they got to make sure it's the correct, is it milligrams, I don't know, of chocolate, then peanut butter, then chocolate. And if it's not, that is when they're going to shut down the machines because something is broken. So they're having to destroy the product to make sure it's still okay, right? They don't want to destroy one more candy bar than they have to, because that cuts into their profit. So sampling is critical to a company like Hershey to be able to do their quality control, but basically still stay in business. Now, you're not going to be able to tour the Hershey factory, but if you wanted just a little idea of an assembly line to watch and a little bit of quality control built in, Bold Rock Cidery down 151 in Nelson County has nothing to do with drinking cider. It's a very pretty place. They have food. There's a stream in the back. But if you ever go, that is where they actually bottle their cider. So I've got to watch them 3 times. Obviously, it's a very small production there. The assembly line is sort of set up like a horseshoe shape. And let's see, the bottles are empty. They're washed. Then they go around. The Bold Rock label is slapped on from a machine. A machine puts the label on the glass bottle. Then it goes and it gets filled up with whatever flavor they're bottling, in that hour or two. Then it comes around and it gets crimped, the little top that gets crimped on there. Then it gets to the human at the end. And I've only watched for probably 10 minutes total. And the human, he's going very fast. But he's looking for a couple things. Sometimes the little Bold Rock label has been put on crooked. It's like all diagonal. It doesn't look right. He takes those bottles out. That's going to be an easy fix, right? They'll be able to rework that. Sometimes the bottles, they didn't get filled up all the way. So he pulls those out because nobody's going to buy it off the shelf if it's not filled up. So those were quick quality controls that he did with his eyes, and I got to watch that. Now, I don't know enough about Bold Rock like I do Hershey, but at some point they're going to do quality control checks on that product, not, making sure it tastes right, but they're also got to check the alcohol content and all of that, and that is going to destroy the product. So at Bold Rock, it's a quick little way to watch a little bit of quality control in anything that is manufactured. All right, first activity. You can, once I explain what to do, you can pause me. It would be nice if you timed yourself. I'm trying to recreate when we do this in the classroom, even though I'm not going to be able to get the data from you, right? But if you want to see how you would have done, I'm going to after you guys do this, I'm just going to give you an idea of how classes tend to do on this activity in the past. But this is a typed little nonsense paragraph. Do not use pencil, but time yourself 2 minutes, and you have to count the number of F's that you see on this piece of paper. Well, not up here. This was when I was Xeroxing it near my keyboard, just in that nonsense paragraph. You are counting the number of F's, okay? So you go do that for 2 minutes and then come back. Okay, so I would then collect all the data from you. Most students, I usually get at least 1 or 2 that counted 37 all the way up to 48. So sometimes I'll have 1 student there, maybe 1 student there. I literally am making up numbers now, but I've done this so long that I have a feeling for what most people do. All right, let's see, 2, 4, 8, 8, 8, 16, 20. So let's say that was my 25 people, okay? How many F's did you count? So I wanted to present this. See how I organized it into a table? There was no reason to start at 0 because I'm sure everybody saw at least 1 F, right? So that's why I usually will ask the class, who's got the lowest amount, because that's what I have to start with. No one is going to tell me they have half of an F, right? You can't. That's ridiculous. You'll see in a few minutes in this video, this is going to be called discrete numerical data, because everybody has a number. Everybody actually has an integer to tell me, and that's what discrete numerical means. And this is always a fancy word that people forget what it means. Frequency distribution, all that means is a table. That's all that word means. So, to let you know, the correct answer is 48. No one hardly ever gets that. I did not get that when I did this activity. I usually will add in the people who were close. So, 5 out of 25, which happens to be a nice 20%, okay? I actually usually don't get that many. I made a nice class here. The point of this activity is to show that even when we're relaxed and we're not sick of our job yet, this is an objective activity. We all knew what an F looked like. It was not my handwriting and it was typed. And we as humans still can't count the number of F's. So just to make you a little cynical, when you're reading studies and data that comes from studies, and if something doesn't seem right, always remember humans can make mistakes, not because they're meaning to, just honest to goodness mistakes. Also, think about all the subjective data collections out there, anything in the medical profession. I always use this as an example since I'm getting older. Well, I don't seem to have a spot on my arm right now, but let's say there's a spot on my arm. I could go to different doctors. Is it just an age spot? Is it a little rash? Is it some form of skin cancer? What type? How far along? I might actually get different opinions from different doctors because it's very subjective. We are not even able to do an objective activity correctly. So keep that in mind with any type of subjective data collection. All right. Now so most of 207 is talking about numerical data because we can do so much more with numerical data. They're numbers, right? Than we can with categorical. Honestly, the people that do the most with categorical are elementary teachers. Y'all do a fantastic job. I wish that somehow in grades 5 through 12 they kept it up, because then when I get my students into college, they have forgotten everything that they know about categorical data. But let's talk about the different types of data we have, and then talk about how we can present categorical data. Okay, the two main types of data we have are categorical versus numerical. Fancy word for categorical is qualitative. Fancy word for numerical is quantitative. The really easy way to remember this is categorical is words, numerical is numbers. I swear to you, it's as easy as that. If you look at the survey, I apparently asked them 3 variables that they gave me numbers as an answer, right? Then I asked 3 other variables that they gave me a word. Yes, no, sorta, something like that. So, gender is categorical. You would tell me you were male or female. Color of your eyes is categorical. Blue, brown, hazel, black, whatever. Some weird ones. I have the luxury of different colors here. Zip code. So if you ever get a weird one and you're trying to decide what type of data, ask yourself, would calculating the average zip code make sense? Would I add up 5 zip codes and divide by 5 and state the average zip code? Yeah, that does not make a bit of sense, right? Zip code is really just representing, a land mass or something. So zip code is categorical. What about if I really don't want to know how old you are? I just want to know how much to charge you for your dinner or for a Busch Gardens ticket or a movie ticket. I just need to know, are you an adult, a child, or a senior citizen, so I know what button to hit on the register. I just want to know which of those 3 categories you fall into. Those are the 3 words you would answer me, right? I don't care about your numerical number. So if you're using it like that, that is a way to make it categorical. Now, numerical gets slightly more complicated because we have 2 different types of numbers. I think your book even says, oh, we're not going to talk about this again because we already talked about it in chapter 15 or something, or chapter 3, I don't know, but we're talking about it because this is going to help us decide what type of graphs to do in the next video. We have discrete. Quick way to remember that is counting. And then we have continuous. Quick way to remember that is potential for decimals. Okay, continuous versus discrete. So discrete, well, you just gave me discrete data a minute ago. How many F's did you count? How many cats do you own? No one has half a cat at home, right? There's no way to get a decimal. How many chairs are in the classroom? No one's going to count half of a chair or a quarter of a chair. No one can come along and count my cats more precisely than me. One that maybe some people get confused on is money. I know this is even debated on the internet, and the debate is wrong. Think about it. If I have $3.12, some people are going to think, oh, you wrote a decimal. Yes, but think about an American money system. The penny is as small as I can go, right? So $3.12. No one can come count my $3.12 any more precisely than me. They can't get more precise. Maybe an even easier way, turn my $3.12 into how many pennies do you have. You can always turn it into counting pennies, and now it's just like counting cats. You're not going to have a half a penny. I would have 312 pennies. Continuous, honestly, most data in real life is continuous because it's measurements. Well, that's the definition, not a variable. We could do volume, height, length, all that stuff that someone can get more precise, if they have a fancy measuring tool, a laser, hooked up to a computer or something. How long did you study for my test? You might say 20 minutes. No, you didn't. I seriously doubt it was exactly 20 minutes. It may have been 20.32 minutes or something. So this is why age is continuous. You can imagine starting a stopwatch right when you're born, stopping it right at this moment, and it's going to be able to tell you precisely down to the millisecond exactly how old you are. It's just like measuring any of these things more precisely. All right. Okay. Oh, maybe just another quick comment, because sometimes students get confused between the variable and the value of the variable. So, if the variable is what is your gender, then you could tell me male or female. If the variable is birth month, well, there are 12 values that could take, right? January, February, all the way up to December. So what is your birth month? What is your gender? Those are variables. These are just values of the variable. Number of Facebook friends, I guess that could run 0 to, well, technically infinity, but whoever has the most Facebook friends, I don't know. All right, let's actually talk about displaying and organizing categorical data. This is in chapter 30.1. There's really only 3 ways, because I'm not going back to pictograms and those things that we might do with kindergartners. You can use a frequency distribution, bar chart, or pie chart. Frequency distribution is just a table listing all the categories and corresponding counts. A few minutes ago, we did a frequency distribution for numerical data. You can do a frequency distribution for categorical data also. We're going to do an example about how spring students thought about cats in just a minute. But sometimes, even looking, well, no, I'll hold off on that thought. When we did the F thing a minute ago, I had 5 out of 25. That's not that bad a fraction, but what about if it's something like 17 out of 43? Most people cannot wrap their minds around fractions. If things are halves and quarters, they're pretty good. When you start getting into thirds or something out of 43, they have no idea what that means. So very often, we like to calculate relative frequency, which is frequency divided by n. N is always sample size in statistics, right? But I want to look here, because here's another spot for confusion. This is out of the unit whole. This is a proportion. 5 out of 25, 17 out of 43, whatever. It is a number less than 1. It is out of the unit whole. Also, I'm going to want 4 decimal places. I'll show you that in a minute. Now, this is not percent. This is decimal form. Now, of course, you always have the option of turning it into a percent if you want. When we do our example, again, I'm going to show you, but sorry, I'm looking ahead, and the example's not going to be the best one because they're pretty clean decimals, but let's just do a quick one right here. That example I just did, I just made that up in my head, right? 17 divided by 43. Most people have no idea what that is. Well, let's see, it's 0.3953. I'm going to want 4 decimal places. Then if you want, you can turn that into percent. And particularly for my future teachers, I know that y'all are going to be teaching kids. And I know that you're going to have them round to the nearest one. I get it. But I'm teaching college students, right? You are not going to tell me that it's 40% or 39%. It's 39.53%. I think I probably got you in a pretty good habit of that when we did the probability unit of 207. So that is back again. Speaking of probability, if you're feeling a little deja vu, relative frequency really is probability. Those two words are very synonymous together. All right, I need a few more notes first before we do our example. Sometimes the table can even get a bit cumbersome. If I was asking people what month you're born in, nobody wants to look at a table with 12 entries, January through December, right? Your eyes are still going to have to be going up and down. So that's what graphs are for. Graphs are the idea that I should be able to look at a graph and get everything in one look of my eye, right? So that's what a bar chart is. It's just a graph of the frequency or the relative frequency distribution. Not that many rules. Your bars have to have equal width. Think about why that is. When you look at a graph, you're really seeing 2 dimensions, right? Your eye is seeing the area, length times width. So if we're keeping the bars the same width, if our eye is seeing a difference, that's going to be the height of it representing the frequency. You have to have spaces between the bars. Just in case you want to look at some in the book, I'm going to show you real life ones that I've come across in my real life, but there are some other examples of bad bar charts in the book on page 677. I'll show you my pictures after we do the example. Let's see what Spring thought about cats. I allowed them to answer yes, no, or I did a little catch-all kind of sorta that for some reason they couldn't decide between yes and no. So we took our ordered column of do you like cats? I've already counted up how many no's, how many sortas, and how many yeses. Okay, so I'm just counting up. Those were my frequencies. So my N is 40. Now, 12 out of 40. Most Americans are going to have trouble with that. So, probably better to calculate the relative frequency. Now, again, just because of coincidence, these numbers turn out real nice. I don't technically need these zeros, but I'm just trying to show you how I do want 4 decimal places. All relative frequencies should add up to approximately 1 because we're talking out of the unit whole, right? So at this point, this right here is called a frequency distribution or a relative frequency distribution. Now, let's make a bar chart. I know some students are a little worried about how to deal with the decimals, so let me show you. We're just trying to get a quick sketch because that's what computers are for, to be perfect, right? I got to get up to 0.6. 1, 2, 3, 4, 5, 6. How about that? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So I had, this is yes. I've gotten myself writing too small. So that's yes. No is 0.3. I got my spaces. That's my no. And the ones who couldn't decide, the sorta. Okay, just a quick sketch by hand. Yeah, maybe this will make more sense if I talk about the pie chart. Then I'll show you my examples of bad bar charts. So again, pie charts are not that different from spinners. They're all based on that central angle, 360 degrees, right? So let's say the book or me ask you to make a pie chart. We're not getting out our geometric tools, okay? I would just ask you for the degrees. So let's make, do you like cats? Yes, no, sorta. But if we were doing a pie chart, I want you to tell me how many degrees. Now, we've already done this relative frequency. 60% like cats. So I just have to figure out what is 60% of 360 degrees. Remember, of in mathematics means multiply. Sorry, I'm just trying to give her more room. So 0.6 times 360 is 216 degrees. 30% said no, they don't like cats. 0.3 times 360, 108 degrees. 10%, 0.1 times 360 is 36 degrees. And if you're afraid you've made a mistake, add those up, and it absolutely should add to the 360 degrees. So basically, it's your relative frequency in decimal form times 360. That's what gives you the degrees, right? So that's all you would have to do for me. You wouldn't have to actually draw it because none of us are very good at drawing 216 degrees really quick, right? All right, so, all of my stats classes probably wonder, why do I take the time to go through bar charts when you guys are doing that with first graders? Definitely all through elementary school. And now I just want to briefly show you why. So hopefully I'll be able to hold things up to the video pretty well. Let me go ahead and get this erased. Now I'll probably hold off on some of my bad stat examples till next time. Let's see. I'm about to pick on everybody. I'm trying to see which one's the better copies. Hold on. Okay, this one's probably better. So this is an example that I found in Reader's Digest myself. It's an easy reading magazine to help me fall asleep. It's Would You Come to America If You Could? 16% of people from India would come to America if they could. 73% of people that's India, that's Russia. I'm having a hard time looking at the laptop and reading this, okay? Now, first of all, I don't have a problem that they didn't leave spaces. And I see that they're trying to use cute suitcases, right? Which I don't have a problem with. But look at that 16% suitcase and the 73% suitcase. That suitcase looks, 8 to 10 times as big as that. We did this with middle schoolers one time. We had them cut out the Russian suitcase and then trace it over the India suitcase and count up how many of those tiny suitcases would fit in there. Well, it's way more than it's supposed to, right? I think it should only be about 4 or 5, and they were able to fit like 10 in there. My eye is getting tricked. They not only let the suitcase get taller, they let it get wider, and you can't do that because that messes up the area. Very common. One of my Math 220 students found something in the Breeze newspaper that did the exact same thing. It was cute little football players, attendance at the football stadium. You see this tiny little guy down here, he's about 19,500 or something, and this really big guy over here, he's 25,000. It looks like 10 of those would fit into that. Well, that's not the case. It's not even twice as big. 25,000 is just 1/4 as big as 20,000. So that area proportionality rule, you can't do that. They not only let the football player get taller, they let him get wider. So now the area looks 10 times as big. That is not allowed. They also messed up the goalpost. Was there no one at the Breeze editing department that had taken a stats course to know that that is completely wrong? Let's pick on Target. I love Target, but we're going to pick on them. So Target, a few years ago, for free into the Breeze newspaper, put a colored glossy paper mini magazine. It was like 40 pages long, and it wasn't much advertising. It was recipes to cook in your apartment and how to, interview and write resumes and stuff. And this was one of the graphs here. Now, we see it's a basic bar chart. It's a value bar chart. It's got spaces between the bars. First of all, I don't know where they got their numbers from because no teacher is getting their degree for, what does that say? $12,000. That's just not happening, but just looking at this graph right here. But what really caught my eye is I was able to, sorry, I'm still having trouble looking backwards, to see the 200,000 bar and the 50,000 bar. And I'm like, why isn't the 200,000 bar 4 times as big as the 50,000? I'm like, what did they do wrong? Look, they started the y-axis nice and even, but then, oops, we're running out of room. Let me just jump up to 100,000 and 200,000. You cannot do that. What grade do we teach our students to mark off the axis evenly? They screwed up. Then I feel like they thought, we'll just label the bars so that people can just read it. If you want me to read the information, you put it into a table. You do not make a graph out of it. So this is completely wrong. Pick on VCU for a minute. So VCU has a thing where they put stuff on the back of the bathroom doors to read when we're going to the bathroom. And I wanted to show you, though, there was all of this prose. No one is able to read that when you're going to the bathroom. So I'm just going to show you the graph here. But what's interesting, too, is that normally we're presented with data of who is smoking pot, marijuana. This is who is abstaining, who is not smoking marijuana. So there was the graph. Let's see if I can hold this still enough. And first of all, here, I might have a bigger one. Hold on. There we go. Here's my bigger one. It's much easier to see. I just blew up the graph. First of all, this is a comparative bar chart. Apparently, they did 2 different studies. They gave us like the formal little like letters and names. We don't need to see all that. What I want to do is focus right on this guy, right? Females are the gray, males are the black. So this is who is not smoking pot. I should be able to look at this and say, oh, yeah, the females really have their act together. More than twice as likely for the females to not be doing marijuana than the males. But is that really the case? My eyes should be able to look at these bars right here and make that determination that the females got it together, right? Look at what they did. They started the y-axis at 46%. I truly never thought I would see anyone do that until I saw this coming from VCU. You cannot do that. So if this is 46, I guess the men are about 51, the women are about 59. So yeah, women are 9% more, but let me go back to the whiteboard for a second. Think about it. If you have a bar chart that looks like this, okay? And you can see that that one is 3 times as big. But what some people sometimes do on purpose, I don't think BCU did this on purpose. I think they did it out of ignorance. If you just decide to lop off the axis and not let it start at 0, it's going to look 10 times as big there, right? Let me do one more. Let's say you have these 2 bars. Not much difference at all. But you start the y-axis not at 0. Remember, there wasn't that much difference. That one is going to look 3 times as big. So absolutely cannot do that. These are bar charts going wrong all the time in real life. I think I have 2 more, but let me see if I've... Oh, I'll pick on target again. Let me pick on a pie chart in that same mini magazine that Target sent out. Look at these 2. I mean, that's... Okay, that's probably a 3763. My eyes aren't that great. Look, they used the exact same picture and they just changed the labeling. There is no way this is a 45-55 pie chart. And now I realized they just used the same picture and said, oh, we'll just put different numbers on top. It takes literally 2 minutes to make a pie chart on Excel. They could have made correct pie charts. This was in that Target mini magazine also. And one other thing, because at some point, whether it's your life or you're helping the middle school students or even 5th graders do some science fair project or something like that, they're going to be on Excel. So I want to warn you away and tell you never to use Excel pie charts. Don't ever use, the 3D charts. Do not ever use 3D bar charts or 3D pie charts. There's no reason to. Plenty of times in real life we need 3D graphs. Bar charts and pie charts is not one of them. If you're artistic, you probably already know where I'm going with this. This was from one of my colleagues at JMU. This was what percent A's, B's, C's, D's, F's, and W's we gave to our students. If it is 3 dimensions, you're going to see the front of the bar and the back of the bar. I have no idea which spot I'm supposed to look at. I should not have to Google how to read a 3D bar chart. There's no reason for it. No one knows if you're supposed to look at the part that's closest to you, the lower part, or the backside part. I do not have a picture of the pie chart, but the pie chart gets even worse. If you can imagine a 3-dimensional pie chart, the part that's coming out at you on the computer, you're going to see the thickness of it, right? But the slice that's receding back into the computer, it can be the exact same percent. The one that's receding back can look 1/5 as small, or as big, as the one that's in the front. So stay away from the 3D ones. And unfortunately, it's done in the textbooks all the time. This was out of a grade 3 through 5 workbook I have in my office. And look at that 3D bar chart. And I'm telling you, I don't know how to read it. I don't know if I'm supposed to be looking at the front, which is 8, or the back side, which is 9. I actually don't know what I'm supposed to be looking at, to be honest with you. So this is really bad that our textbooks are in the habit of it. There's absolutely no reason for it. So please stay away from the 3D bar and pie charts. All right. Well, that is probably enough for now. Again, as we go through the next couple of videos, I'll probably show you some of the bad stats stuff. Remember, the nice thing about videos is if you need to take a break, you can always pause them. So work on the homework, then watch the next video.